Hello, AP Physics students. I hope not to be too impulsive with you, but we're going to work out another problem. Little pun there that you're going to understand in just a minute. So, we are going to look at Chapter 7, problem number 16. And as I illuminated to earlier, this problem may have something to do with impulse and momentum. Okay? Okay, so this problem says a 12 kilogram hammer strikes a nail with a velocity of 8.5 meters per second and comes to rest in a time interval of 8 milliseconds. What's the impulse given to nail? What's the average force acting on the nail? Okay, so let's start this problem how we would any problem. All right, so we've got a nail, right? Ooh, there's a good looking nail, right? And we've got a big old hammer, right? All right, hammer time. Okay. All right, and we know that the mass of our hammer is 12.0 kilograms, which is a really big hammer. That's like a 25-pound hammer. We know that the velocity of the hammer right before it hits the nail is 8.5 meters per second. We know the time over which the hammer comes to rest is 8 milliseconds, right? So I like good old-fashioned units, right? I like to put things in seconds and meters and kilograms. So I'm going to just switch that 8 milliseconds to 0.008 seconds. All right, so it wants to know what the impulse is and what the average force is. All right. Okay, well, Mr. Gersden, I don't even know what impulse is. How am I supposed to solve for it? Great question. Okay, what is impulse? Impulse is an average force uh, exerted over a certain time interval. Okay, so impulse is average force times time. And a lot of times we talk about impulse when we're dealing with short time intervals. So there's a nice graph in your book that looks something like this. When you're dealing with some type of collision, right? Like a baseball hitting a bat or a hammer hitting a nail. A lot of times what you get is a graph that looks like this. Some spiking type of force over some very short time interval. And the force changes so rapidly that it's really difficult to calculate. So what we do instead is calculate some type of average force and multiply it by time. And this product of average force times time is actually the area underneath the curve here. And we call this product of average force times time impulse. All right. So impulse, the units for impulse are Newton seconds. Okay. Newton seconds, right? Kind of makes sense. So impulse is a vector quantity and it points in the same direction as the force does. Okay. So for instance, in this diagram, since a force is an interaction between two objects, this would be the force that the hammer exerts on the nail, right? And this would be the force that the nail exerts back on the hammer, right? Okay, so if we're talking about the impulse that the hammer imparts on the nail, it would be pointed downward here. So impulse is average force times time. So that's a definition, but where it's useful is we can say that impulse is equal to the change in momentum of an object. Okay, so this is going to be very useful in this solving this problem in particular. Okay, so I am going to figure out the impulse that the nail exerts on the hammer by doing the following, by doing mvf minus mvi. Okay, so this is the change in momentum of the hammer. All right, and I'm going to find the impulse by calculating the change in momentum in the hammer. Okay, so mass of the hammer, 12 kilograms. Final velocity of the hammer, 0. Mass of the hammer, 12. Initial velocity, 8.5 meters per second. Okay, so if I multiply this out, I get negative 100 kilograms times meters per second is the impulse, right? Okay, so 100 kilogram meters per second is the impulse. So we should say a direction here. Actually, we should read the problem and double check what it wants us to know. It says, what is the impulse given to the nail? So the impulse given to the nail would be 100 kilograms meters per second downward. Right? That would be the impulse given to the nail. All right? So that's our answer for part A. All right? The impulse given to the nail. Okay, so let's dive into part B here. Before we do that, just a little bit of a technical difficulty. Our book uses I to represent impulse, but the AP equation sheet uses J. Oh my gosh, Mr. Kirsten, that is confusing. Well, if you ever get confused on what J means, it means impulse. You can always look over here. I never knew why they use J for impulse. A capital letter I works pretty good to me, but do be aware of that. All right. Okay, so in part B, the question is asked, well, what's the average force between the hammer and nail? Well, if impulse is average force times the time over which that force acts, I can say, hey, the average force is the impulse divided by the time, okay? Notice impulse and average force would be in the same direction by vector quantities, okay? So the average force would be equal to the impulse, 100 kilogram meters per second, divided by the time, 0.008 seconds, all right? That gives us an average force of 13,400 newtons, all right? Okay, and what direction is that force? Well, the question says, what is the average force acting on the nail? So since we're talking about the force acting on the nail, that force is directed downward. Okay? All right. Now, some of you may be questioning my units here a little bit. You know, this impulse, it should be in Newton seconds, and this time is in seconds, so that works out. Now, are the units right in this equation? I mean, after all, a change in momentum should be kilogram meters per second, whereas impulse is in Newton seconds, right? Are these really the same units? Well, as it turns out, yes, they are. Remember, a Newton is a kilogram times meters per second squared, so a Newton second would be a kilograms times meters per second squared times second, and those cancel. So yes, indeed, a Newton second is indeed equal to a kilogram meters per second. In other words, a unit of impulse is equal to a unit of momentum. All right? Okay, nice work, AP Physics students here. We're going to get you your joke here for your reward. All right, so today's joke comes from the internet, from the website XKCD, which has great science stick figure humor, which is my favorite type. And here we go. It looks like we have James Bond on a centripetal force machine and an evil mastermind saying, "How do you like my centrifuge, Mr. Bond? When I throw this lever, you'll feel centrifugal force crush every bone in your body. And Mr. Bond, using correct AP Physics terms, says, "You mean centripetal force. There is no such thing as centrifugal force." And the evil villain says, "A laughable claim, Mr. Bond, perpetuated by overzealous teachers of science. Simple construct Newton's laws in a rotating system and you'll see a centrifugal force term appears as plain as day." Come on now, do you really expect me to coordinate substitution in my head while strapped to a centrifuge? No, Mr. Bond, I expect you to die. Oh, the coordination of centrifugal versus centripetal force with a cartoon involving James Bond. Oh, it's too funny, too funny. All right, nice work, AP Physics students.